we're going to extend the idea that we've just seen about multiplying complex numbers together to consider what happens if you raise a complex number to a power. But first, we're just going to consider a straightforward algebraic expression of the form a e to the b. So we've got the a multiplied by the e to the b. If I now take that expression and raise it to the power of n, then because the element inside the bracket is a product, I'm going to end up with a to the power of n multiplied by, now by the laws of indices, I've got e to the b all raised to the power of n. I'm going to multiply those two indices together, so I have e to the power of the product nb. We've established that we can express a complex number z in the form re to the I theta, which is exactly the same idea as the expression I had above. So if I want to find out how to simplify that complex number raised to the power of n in exponential form, I can do it the same way. So I can raise the r to the power of n. This gives me the modulus of the product. Sorry, the modulus of the new complex number raised to the power. And when I consider the other part, I get e to the I n theta. So I have that the argument of the new complex number is n theta. So this new complex number z to the n has a modulus r to the n and an argument n theta. So the modulus is raised to the power of n, whereas the argument is multiplied by n. If I write this in modulus argument form, if z equals r lots of cos theta plus I sine theta modulus r argument theta, then z to the n is equivalent to r to the n cos of n theta plus I sine n theta. So I have my new argument n theta, so the argument is multiplied by the n value, whereas the modulus is raised to the power of n. Okay, and this rather important idea, which I'll put some red boxes around, is known as de Moivre's theorem, because it was discovered by a guy called, I believe, Abraham de Moivre. Okay, and the first thing we're going to do with this is just check that we're happy using this to simplify an expression for a complex number. So if I take the complex number z equals 2 cos 2 pi over 3 plus I sine 2 pi over 3, and I'm looking to simplify an expression for z to the 5, where z has the definition above. So z to the 5. So the n value is 5, so I need to take the modulus of the original complex number and raise that to the power of 5, so that's my new modulus. And I need to take the argument of the original complex number z and multiply that by 5. So I'm going to get 2 to the 5 lots of cos. New argument is 2 pi over 3 times 2 pi over 3 times 5, which gives me 10 pi over 3 plus I sine, obviously the same argument here, 10 pi over 3. Now that's lovely, except that 10 pi over 3 is not in the range that we specified for a complex numbers argument. So going back to the beginning, 2 to the 5 has a specific value 32. Cos of 10 pi over 3 is out of range, so I'm just going to subtract entire rotations of 2 pi until I get to something between negative pi and pi. So I'm going to subtract 12 pi over 3, and that's going to give me a principal value of the argument of this complex number of negative 2 pi over 3 plus I sine negative 2 pi over 3. So that's just simplifying one power of a complex number, but the bit in the red box is the idea that you need to take away.